Hello everyone, Mr. Keeney again. We're going to be doing our second section of notes for Algebra Geometry 2. Our learning target for this unit is we are using vocabulary based on the undefined terms to develop the foundations of geometry, which that right there is our unit title actually. So we're still working on what we learned in our first section of notes, and we're going to be building upon it. And today specifically, we're going to be talking about the segment addition postulate. Now, before we talk about what is the segment addition postulate, I want you to more focus on what is a postulate, because that might be a new word for some of us, and it is very related to another word that you might have heard before. So I've highlighted postulate, and it is related, not the same, but kind of related to a theorem. So let's talk about the differences. A postulate is a rule that's accepted without proof. So I'm going to underline without proof. We just accept it. We do not need to prove it. We do not need to show justification. It's a lot like when we talk about the undefined terms. There's no definition. It's not defined. We can describe it, but we will not have a definition for it. Same thing goes with a postulate. We are accepting it without proof, and how that relates to a theorem is it is a rule still, but a theorem is a rule that's proven. And a lot of times we use postulates to prove theorems. So postulate, what we're going to talk about with segment addition postulate is a rule about segment addition that we do not have to prove, that we just accept. Here's a good example of another postulate too. It's called the ruler postulate. The points on a line can be matched to 1 and 1 with real numbers. The real number that corresponds to a point is the coordinate of a point. So I'm going to coordinate of a point. So basically what we see, and you've seen this before on any kind of number line, if we were to have these 2 points here, and I'm talking about A and B, if we have those 2 points, a lot of times instead of seeing x1 and x2, we might see an actual number value. So we might see something like 3 or 4, and the number line what I'm talking about is just a simple one that we've seen in math quite a bit, where it counts or uses our counting numbers. So we have a ruler postulate that says if a point is on one of these corresponding numbers or real numbers, we would say B, for example, here, or maybe not B because we've used B, C, where C is at 1. And here's the big thing with the ruler postulate, because that's kind of accepted, and we get that. We're going to be talking a lot today about distance or length. The distance between points A and B is written as AB, that's kind of important, and it is the absolute value of the difference between the coordinates A and B. So if you see our picture down here, we have 2 points A and B, and the distance from A to B is x2 minus x1, but not just the x2 minus x1, the absolute value. So I'm going to try to give you an example. Let's say this one right here is at 6, this one is at 8, and I want to find the distance from A to B. Well, it tells me if I want to find the distance from A to B, I would take the absolute value of x2, which was 8, away from 6, and we would get our absolute value, our distance. So 8 minus 6, that would be 2, and the absolute value of 2 is 2. So our distance of segment AB is 2 units. So I do want to point out one other thing here. When you see AB, that is a little bit different than what we see with this right here, what we talked about in Unit 1. If I were to talk about AB, this is saying distance from A to B. That's how we'd want to read it out loud in our mind. This one is simply saying segment AB. So those are kind of the two differences. Why is there a bar? Well, that's talking about the actual segment. We use that with congruence. If we have just AB, we're talking about the distance from point to point. Segment addition postulate. So here's another one of those rules that we accept without proof, which says if B is between A and C, then AB plus BC equals AC. And you see this nice little picture over there that kind of illustrates it. If AB plus BC equals AC, then B is between A and C, so it's kind of the converse there. So we're going to be using this idea, and I guess should point out here that what they're saying is part plus part equals whole. Well, there can be more than 2 parts, but oops, in this general statement here, part plus part equals whole. So if I were to take AB plus BC, you're going to see that it gets me the whole AC. So we're going to take this idea and apply it to some examples. So this first one says find xz. So if I want to find xz, which is this right here, this whole length, and I'm looking for that length, what the segment addition postulate tells me is that, okay, I don't know the whole thing, but I do know, if I can change colors, I do know this part, which that is xy, and I do know its other part, yz. Oops. So if I were to take those two values and add them together, I should get the whole xz, which is what we're going to do. So xz equals, I can see that xy over here is 7 plus yz, which is 12. From here, we're just using a little bit of our algebra rules, combine like terms. Xz equals 7 plus 12 is 19. And if they do not give us units as far as like centimeters or inches, we are just going to write units. So Xz equals 19 units. All right. Here's another example for this one. It says find RS, and this one's a little bit different. So I'm going to go ahead and set up kind of what the segment of postulate says. It says the whole thing RS, or excuse me, it doesn't say the whole thing RS. It says the whole thing QS, QS being this entire segment. QS would be equal to QR plus RS. So I do know some things about this situation, but not exactly like the last one. For example, QS, like I said, is this whole thing. I know that it's 22, so I actually know what the whole is. I also know what QR is. QR is right here. It's 9. What I don't know is RS, but luckily for us, that is what we're trying to find. So I would take away 9 from both sides because I'm trying to isolate the RS, and I would get 13 equals RS. So we've solved this equation, and for our final answer, to make sure our notation is nice and beautiful and pretty, we would put the units on the side. So RS equals 13 units. And we got one more of these kind of examples here. In this one, we're using JK. Oh, excuse me. I keep saying using JK. We're finding JK. And what I know from the segment addition postulate is that this whole here is equal to the sum of its parts. So JL is equal to JK plus KL. I do kind of just want to show you real quick how I'm getting this. JL is this whole length. JK is this length. KL is that length. So you can see if I take those two parts, I'm going to be ending up getting the whole. And now I'm just going to substitute in what I know. For JK, I see that I have 2x. So JL equals 2x. And for KL, I say I have 4x plus 3. But that's not exactly all I have either. I forgot up here for JL, I know it's 33. So I'm going to take JL out and put 33. And if I'm trying to find JK, and you'll see over here, JK is defined as 2x. Before I find JK, I need to find x. So this is what this equation over here is to do. We have like terms, so I'm going to go ahead and combine those. 33 equals 2x plus 4x is 6x. And then bring down the plus 3. I'm going to take away 3 from both sides. I have 30 equals 6x. Divide by 6, and I get, and I'll have to put it over here, but that's okay. I get x on one side, and 30 divided by 6 is 5. Now that is not our final answer. Remember over here, our final answer, we want to find JK. So for JK we said is equal to 2x. But now I know what x is. X, you can see down here, x is 5. So I'm going to say 2 times 5 now, and 2 times 5 is 10. So JK equals 10 units. And that would be our final answer. All right, so those are the 3 example problems, and we're going to go over some of those more together. And the last thing we have is talking about congruent segments. And I've kind of mentioned this before with notice on these ones here. there's no bar. So they're talking about equality. They're talking about distance. They're talking about lengths right here. The distance from A to B is equal to the distance from C to D. If we are talking about congruency and we have bars, we are talking about the actual segments. And the segments, we say, are congruent to each other. When you see congruence, I want you to think of the word same. They are copies of each other. I could take one and put it right on top of another one. So those are just little notation things for us to focus on as we talk about more topics in this first unit. In our last example here, went too far, is graph the points x, -2, 5, y, -2, 3, and we got two other points, w and z, in the coordinate plane. And we're going to see, are they congruent? So let's go ahead and graph these points, -2, -5, 2, 3, 4, 5. I got to count. You count out loud like me? That is okay. Y is -2, 3. 1, 2, 3. That's y. And I'm going to go ahead and connect these up. Let's switch colors. We haven't done purple. W now is -4, 3. 1, 2, 3, 4. 1, 2, 3. Uh-oh. We're going to have to get rid of this y here, but that's fine. Oh, and I got rid of my 0.2. So that's W. And then Z is 4, 3. 1, 2, 3, 4. 1, 2, 3. So that is Z. Oh, I put a little dash there. You'll see me do that sometimes. And let's get this Y. All right, so what we want to do to see is if they're congruent, and you'll see up here, congruent segments, what the definition of congruence is. They are line segments, and just to check, we have two segments here. Now, what makes them congruent? They have the same length. All right, so now we know what to do. We are going to go and check the length of these segments. So there's a couple ways we can do this here. I'm going to recommend for you all while you're starting is just to count it out. So if I want to find the distance of xy, I would just simply count out from 1, 2, 3, 4, 5, 6, 7, 8. Another way you can do is the way we talked about earlier, where you can take the absolute value of these two. So that would be like the -5 value and 3. So if I did the absolute value of 3 minus -5, I would get 8. If you do not like that method, that is fine as well. And we'll have these counting options. And then the next one, and our last one here, I would do the same thing. 1, 2, 3, 4, 5, 6, 7, 8. So I would also get 8 units for WZ. And so our final answer, are these segments congruent? Let's check up here. They're segments that have the same length. So we will check, did we get the same length? We did, we got 8 and 8. So for our final answer, we can say that segment XY is congruent to segment WZ. All right, and that ends our second section of notes. Thank you for watching, and we'll be talking about this more